Hey everybody. Instead of finding a video on math, I decided I wanted to make one. I talk about this a lot because math, and specifically number bases, is really fun and it's a core part of understanding computer networking. I've explained this to a number of people. So, number bases are basically talking about how we're representing numbers when we put digits in a string together. Now, you're probably used to, say, the number 157 looking like this, but do you know why those numbers are in that order? It's because they're representing amounts of powers of 10. We call this the decimal system. Deci, like deciliter or decimal, we have powers of 10, referring to 10. I believe it's either Greek or Latin. A linguist could probably tell you. So this is representing the ones column, or 10 to the 0. This is representing the 10 to the 1 first power, or 10 column. This is representing the 10 to the 3 column, or 100s. And unless you are, say, teaching an elementary school kid math, and you're talking about 10 frames and filling them up, you probably don't think about this too much. But there are other number-based systems, and we use some of them all the time. The one we use all the time that you might not realize is binary. Now, binary is a much more basic number system than decimal. Binary refers to by or two. So we're only talking about powers of 2. So let's do our powers of 2. 2 to the 0 is again 1. That's the identity there. 2 to the 1 is 2. Or that's the identity. But, 2 to the 2 is 4. We keep going. 8, 16, 32, 64. And way over here, 128. Hope you can see that. That's 2 to the power of 7. Now, there's a reason I chose 8 spots here. And that's because we use that in a lot of places with computers, because computers only really know on and off. Early on computers, they tried to do things with vacuum tubes that had intermediate states, but once we switched to transistors, which were much smaller and more efficient, they could only really do on or off. And everything a computer knows is either just on or off in fancier and fancier ways. Computer processing units, CPUs, are just massively dense banks of transistors switching on and off. So let's talk about a binary number. So again, we're going to use these 8 digits. Let's say, again, that 157. So we had 1, 2, 3, 4, 5, 6, 7, 8 places. Now, to convert 157 in decimal, 10x, 157, we need to count our numbers of 128s. So let's use a little math. So 157 minus 128. We have 29 remaining, so we put 1 in the 128. Now the next would be 64. 64 is bigger than 29. 32 is bigger than 29. We put zeros there. But next down we have 16. That leaves us a remainder of 13. Well, below 16 is 8. So let's take out 8. There's our 8s. We have a remainder of 5. Let's take out 4. We have a remainder of 1. 2 is bigger than 1. We got to put a 0 there. And now we have 1. So in binary, this number here is the same 0, 0, 1, 1, 1, 0, 1 as this number here. But what does that mean to you? Why do you care? Well, you use a binary number a lot of the time, especially if you're a system administrator. It's a real special one. And I am going to write it down for you. And you might recognize this after I translate it to decimal. So this is going to be 1, 1, 0, 0, 0, 0, 0, 0. Let's see. Then we have a 1, 0, 1, 0, 1, 0, 0, 0. A whole bunch of 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Now, we call each of these groups of 8 a byte that consists of 8 bits, or binary digit bit. Now, what is this number? And why do I say you might use it every single day? Well, this first one, 128 plus 64 is 192. 128 plus 32 plus 8 is 168. 0 is, of course, 0. And 1 is a simple one. That's just 1. 192.168.0.1 is probably the IPv4 IP address of your home router. Or it might be .1.1. But we're going to talk about this. Now, when you see this number, especially if you do any networking, you might have encountered it written with a network definition or a subnet mask. So what is that number? Why is that the way it is? And why does that mean the same thing as 255.255.255.0? What? Well, that's because when they say subnet mask, they really mean it. It's literally a mask that shows you which of these digits are part of the network or subnet and which are the part of the host section. Network ID and the individual hosts on that network. So the way they do it, 24, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That makes 16. 1, 2, 3, 4, 5, 6, 7, 8. That makes 24. Now, I know the zeros are trailing off over here, but that's part of the network mask. So this is showing us that this and this and this are all part of the network definition, and this over here are the hosts. So we can have 255 hosts minus the network ID, which is 0, minus the broadcast, which is 255, the all ones. So we have 250. Well, we count 0. When we count up to that 255, we have a total of 256 digits. So we have 254 available network addresses because the broadcast eats one. Now, what happens if we need more than that? Well, we could, instead of doing what this is a /24 is a class C, we could take a whole nother chunk, turn all these to zeros, 0, and call it class B /16, or take all these and turn them to 0 as well. Class A is 8. But what if you don't need all that? What if you only need double the number of hosts? Well, you might have seen subnet masks that are classless, also called CIDR, CIDR, classless interdomain routing. And for example, /22, well, all we do is we turn 2 of these nice little guys here into 0, 0, 0. And now we've carved out this part so that it's not part of the network anymore, and it is instead part of the hosts. And that means instead of 254 hosts, we have double that and then double that for somewhere just under 1,024 hosts. I believe I've got the math right. And that's why we care about binary, because computers think in binary, and I wouldn't want to have to type this in along with that every time I typed an IP address. I like typing this. It's easier to remember. But what happens if numbers are really, really big? Well, let's talk a little bit about octal first, because that was the first way earlier system design used bases to help numbers be easier to handle for humans. So that's base 8. So instead of 1 and 0 for 2s, or 1, 2, 3, 4, 5, 6, 7, 8, 9 for 10, we used digits 1 through 7. So that would be 8 to the 0 is 1, 8 to the 1 is 8, 8 to the 2 is 64. And it goes upwards from there. So, so let's see. I've got to think here. 64 plus. I have to go one farther to get to our 157 example. So 8 to the third is 512. Wait, no, I don't have to go one farther. I'm wrong. So, since we are not counting in binary anymore, we can count up to 7 digits in each of these places. So if I wanted, for example, the number 8, well, I don't go and put an 8 here in the ones, nope, that's not going to work. 8 doesn't exist in this number scheme. I would put a 0 here and a 1 here, and this 1 0 is 1 8 and 0 1s. That's 8. 9 would be like this. So how do we get to our example of decimal 157? Well, we're going to need a couple of 64s. So what's 2 64s do it? 2 64s gives us 128. I think we're probably correct there. So 2 64s. So we got one, let's put the math over here. 157 minus 128. Does that leave us less than 64? Sure does. Leaves us 29. 8 and 8 is 16, 17, 18, 19, 20. So about 3/8 leaves us 24. 24 subtracted from that 21 leaves us 5. So in octal, and actually I'm writing these wrong. This should be, I think, O base 8. Well, either way, in octal, our decimal 157 would be written 235. And though that is a little more cumbersome than decimal for us, when you're working with a lot of binary numbers, notice that these numbers, 1, 8, 64, 8 to the third was 512. These, which is double 256, these numbers are much more similar to binary numbers than decimal numbers are. It makes the math a little easier to convert quickly when you're having to work in a lot of binary. Now, we don't use octal so much because we have even bigger numbers now. We have hexadecimal. So we've got binary, octal, decimal. Hexadecimal has the word decimal in it, but it also has hexa. Decimal, hex for 6. So we're using a base 16. So that means 16 to the 0 is 1. 16 to the 1 is 16. 16 to the second is, I believe, 512. Let's do the math. Yay, math. Clear. 16 squared. Oh, 256. 256. So let's do our 157 again. 157 is less than 256, so it's got to be some subset of this 16. So 157. Let's make a guess. Let's clear this. Let's say it's going to be 16 times 4. 64? 16 times 5. 80. Well, let's jump up. It's not going to be 16 times 10, we know, because that would be 160. If we're trying to get to 157, it's going to be less than that. So it must be 9. 9 16. So what's 9 16? 16 times 9 is 144. So we do 157 minus 144, and we get 13 remaining. But wait a second, we've got a problem. What do we do after we get up to 9? I can't put a 1 over here because that would be too much. Well, we have to use some additional symbols. Instead of just 0 to 1, like binary, or let's put it over here, 0 to 1, or 0 to 7, like octal, or 0 to 9, like decimal, we need some more. So we're going to take the 0 to 9 from decimal and add on A, B, C, D, E, and F. So this 13 would be 9, 10, 11, 12, 13. So our number would be 9D. Not 90, but 9, and then the letter symbol D, in this case acting as the 13 count in the 16 to the 0 place. Now, where have you seen this before? Letters and numbers all mixed together. Well, you might have seen it in IPv6, which uses really big numbers, but you also use it every single day with every one of your devices, and it's printed on the back of them, and you might see like AE19, F2, B0, E3, 1A. 1, 2, 3, 4, 5, 6 pairs. Each of these pairs represents 8 bits, 1 byte. So that's 1, 2, 3, 4, 5, 6 bytes in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 characters, including the somewhat unnecessary for computers but necessary for humans. Nice little colons there. This is a MAC address, or the hardware machine address used in the MAC address layer of TCP/IP networking. So this is what gives your actual network interface card or your wireless card its numeric interface, and it's what Apple machines have started and Android devices have started to rotate. Rather than having a hardware MAC address, they have a rotating pool of MAC addresses. Makes it real complicated for old school networkers. As a final note, so we've talked about 2, 8, 10, and 16, but there are way more number systems out there. I believe the Aztecs used a base 60 system. 60. Who would think? But you use a base 60 system, kind of, and you certainly use a base 12 system every time you look at your clock. 12, 3, 6, 9, and 0 through 59 minutes. We talk about them in decibel numbers, but we are actually using a base 60 remnant for our minutes because it's working in circles, and 60 breaks into a circle really nicely. And 12, base 12 could have been what we used. I believe it was the Sumerians used base 12. Base 12 is really kind of cool. It divides evenly into 2, 6 plus 6, 3, 3 plus 3 plus 3 plus 3, and 4, 4 plus 4 plus 4. Try to do that with your decimal numbers. Well, thanks for talking numbers and networking with me. I've had a really good time, and I hope this has been helpful to all of you. And I've enjoyed class with you. That's supposed to be a thumbs up, and this one's waving. Thank you, and goodbye.